Good morning, respected professors. I am Diwakar Swaroop, fourth year, Department of Mechanical Engineering. My supervisor is Professor N. Datta from Department of Ocean Engineering and Naval Architecture. The title of the group project is In-House Design and Fabrication of Horizontal Axis Wind Turbine. My contribution to the project was basic design, drivetrain design, machinery selection, active control design, tower design, and dynamic analysis. This is what my presentation will comprise of. I will introduce the project with a recap from last semester and then proceed with the work of this semester. Eastern coasts of India are yet to be exploited for wind energy as the wind speeds are not suitable for setting up large wind turbines by big companies. However, small wind turbines can be set up to supply energy to rural households. For proceeding to this goal, a proof of concept in-campus model is developed with the aim to minimize cost of production, weight of structure, use simple machineries, and collect data for analysis. This is the layout of the work done from July 2019. This is a three-member group project and areas of my contribution are highlighted. In autumn 2019, market identification, site inspection, concept and basic design, drivetrain layout, machinery selection, and tower design were done. In spring 2020, there has been a modification in basic design, and accordingly, the tower has been redesigned, followed by its dynamic analysis and yaw system design. Further, the cost estimate was done and the IIT approval was taken. Production contracts have been given in March 2020. The location of the proposed small wind turbine has been chosen as the rooftop of PC Ray Block B, IIT Kharagpur, the tallest structure in the area. The wind data is available for a period of 22 months, making it possible to determine the mean and extreme wind speeds. The most probable wind direction is the northwest. After considering the civil engineering restrictions of the site location, the concept design was initiated. The sequence of power transfer in the wind turbine has been represented. There are three blades which gives the best power coefficient at an achievable tip speed ratio. The rotor diameter is 6.8 meter, which is chosen to capture sufficient power from the wind. The rotational speed of the turbine is 40 rpm. The blades are designed to rotate clockwise while looking downstream. The rated output electrical power at rated wind speed of 4 meter per second is 250 watts. The nacelle of a wind turbine houses the machinery and equipment. The nacelle frame is made up of angles and flat bars and is covered by GFRP. The bed plate at the bottom of the nacelle has all the machineries placed and fixed over it. The bed plate is bolted to the sleeving bearing, making it free to yaw. Starting from the upstream end of the nacelle, first element of the bed plate is the bearing support. Then the manual brake is fitted, followed by the electromagnetic brake. Then there is another bearing support for the main shaft, which leads to the coupling connecting the main shaft to the gearbox and the generator assembly. Finally, the counterweight is present near the downstream end of the nacelle to compensate for any pitch moment and balance about the tower axis. The induction machine is required for converting mechanical energy into electrical energy. In this project, three-phase, four-pole induction machine is chosen. As the machine is directly connected to the main supply, the operating frequency is 50 Hz, making the synchronous speed as 1500 rpm. A typical torque speed curve is shown, where our reason of interest is the negative slip region, where the machine behaves as a generator. The main shaft RPM has to be stepped up to a post-synchronous RPM of the generator shaft. To achieve this high step-up ratio in limited space, the planetary gearbox is selected. The choice of the planetary gearbox depends on the required torque and power transmission and step-up ratio. Accordingly, I chose Agni series B302 planetary gearbox coupled with the induction generator of 0.5 HP, whose drawings have been shown. A manual brake is required to stop the rotation of the turbine at the operator's will. A simple design of the brake is fabricated where two U-clamps are welded to the two jaws of the C-clamp. The U-clamps have an inner asbestos lining. When the handle is rotated to drive the movable jaw towards the fixed jaw, the two U-clamps come closer and the rotating main shaft gets clamped in between them, thereby stopping the rotation of the wind turbine. An electromagnetic brake is the automatic brake of the wind turbine against very high wind speeds. When the rotation of the turbine must stop, when the microcontroller senses a shaft RPM higher than 1700 from the digital tachometer, it signals a DC current to activate the brake and stop the main shaft. The main shaft is majorly subjected to two kinds of stresses: bending stresses due to the weight of the mounted hub and shear stresses due to torque transmission. I have used maximum shear stress failure criteria for shaft design as it holds good for ductile materials. The hub is the element which connects the blade to the main shaft. It transmits the blade aerodynamic torque as a mechanical torque to the main shaft. The hub is designed as a wooden equilateral triangle sandwiched between two mild steel plates. The two mild steel plates are required for bolting the stem to the hub and shaft to the hub. The six aluminum stems are cast into the root of the GFRP blade during the blade fabrication process. The stems are bolted on the mild steel. The main load arising on the bearings of the main shaft is radial load, but a small axial load may also arise. Therefore, the best choice for the bearing support is the deep groove ball bearing, which can sustain both types of load. According to the calculated values of the static load rating and dynamic load rating, I have selected the required bearings from the catalog of SKF company. A coupling is required to connect the main shaft to the gearbox. I have chosen a boost pin flexible coupling for this purpose, as some misalignments might happen in the shafts, which the rigid coupling won't be able to compensate. The rotation of the entire nacelle about the tower axis is known as yawing of the nacelle. Active yaw control system consists of a slewing bearing drive with a mated worm gear between the bed plate and the base plate, a stepper motor to power the slew drive, microcontroller to actuate stepper motor, and an anemometer. Whenever the anemometer senses a wind direction change, it signals the microcontroller, directing it how much to turn the slew drive, such that nacelle is aligned to the new wind direction. The slew drive has to be capable of both anti-clockwise and clockwise rotation. Since the rooftop surface cannot be grouted, it is important to provide a sturdy pedestal foundation on which the tower can self-sustain against extreme weather. Vertical reinforcement steel rods along with 5 layers of horizontal stirrups are provided for supporting each of the 4 M20 concrete pedestals. The monopole tower is welded to the central footplate and reinforced against bending moments by the buttresses, which provide large bending areas. The central footplate is welded to the I-section beams, which are in turn bolted to the footplates on the concrete pedestal. The tower and the I-section beams are designed using the software STAAD Pro. The optimum I-section as designed is obtained as ISMB 175 with a pass ratio of 0.772. In the design of monopole, the main constraint is enough space for slew drive and base plate. It can be seen that in most part of the central footplate, the stresses are well beyond the yield strength and the factor safety is in the range of 5 to 10. For the bed plate, it is seen that the factor of safety is greater than 3 throughout the plate. A large portion of the plate shows no significant deflection. The natural frequencies of the tower are found in ANSYS and validated using the Euler-Bernoulli beam theory. Due to the compressive force of the nacelle weight and its inertia, this frequency comes down significantly. I have also done the time series analysis of the turbulent and gust loads in STAAD Pro for undamped condition and 5% damping. The damping curves down the vibrations and its responses are shown here. A brief discussion of the work done has been presented here. The work started with the site inspection leading to concept design followed by the basic design. The machineries were selected accordingly. The shaft was designed according to various loads on it using the maximum shear stress failure criteria. The bolts were chosen subsequently. Then the entire layout of the bed plate was made with all the detailed dimensions and the sequencing of the dry trim was done. STAAD Pro was used for designing the tower and the I sections. Foundations were designed to ensure safety of tower during the worst load conditions and its dynamic analysis was further carried out. With the detailed design ready, the production is ready to commence. The civil structures have been approved by the CCM. The funding has been granted by IIT Kharagpur and fund booking for the equipments have been done. Blade fabrication materials have been procured and the fabrication has already begun in the workshop of Ocean Engineering Department. The future works include the production, assembly, trial, testing, and the data logging. Finally, I am excited to share that this work has been accepted for publication in top 2 international conferences, namely ASME Power 2020 and ICSB 2020. Finally, I would like to thank all of the people who have contributed towards this project. Thank you for your attention.